All right, so we're going to look at number 7, which is a continuation of 5 and 6, where they were talking about hydrogen gas and neon gas. And they want to know which would have the higher boiling point. And if we were thinking about this, this is obviously an intermolecular forces question. Hydrogen gas interacts with other hydrogen gas through an intermolecular force, and same with neon. So let's predict what sort of intermolecular force it'd have. Well, hydrogen is a nonpolar molecule, so the only type of intermolecular force it's going to have is London dispersion forces. And it turns out that's true for neon too. Neon doesn't even have a bond, so it can't be dipole-dipole or hydrogen bonding. Its strongest intermolecular force is London dispersion forces as well. So remember, London dispersion forces is impacted by the number of electrons in the molecule. So let's look at their answer choices here. Oh, and by the way, neon has it looks like 10 electrons each. Hydrogen, so if this has 10 electrons, and hydrogen only has 1 in each one, so it has 2 electrons. So we're expecting the London dispersion forces in neon to be stronger because there's more polarizable electrons. So let's see. We think hydrogen would have actually a higher boiling point, so that can't be the correct answer. We think neon would have the highest boiling point, so we can get rid of A and C. So the neon, because it has more electrons, that's a possibility. The neon, because it has more protons, no. Remember, it's polarizable electrons that cause something to have stronger London dispersion forces. And then looking at number 8, which gas particles have a higher root mean square velocity? That's what RMS stands for, root mean square velocity. So they're just saying which would have the higher speed. Now you notice that it's really important that they're talking about velocity and not kinetic energy. We know they have the same kinetic energy because they're in the same flask and they're at the same temperature. But the speed of the molecules is going to depend on their size. And neon, being a lot bigger, a lot more massive, is going to have a slower speed than hydrogen, which is less massive. So let's look through our answer choices. A, the hydrogen, we think it definitely would have higher root mean square speed, so we can get rid of right now B and D, because neon is not going to have higher speed. The reason, because it has lower molar mass, that looks pretty good. C, the hydrogen, because it has a larger atomic radius. And so no, we know lower molar mass usually leads to higher speed. Number 9, which of the following compounds would have the highest lattice energy? So I've drawn a lattice down here where we know the positive and negative ions line up in this sort of matrix or lattice. And lattice energy is the amount of energy it takes to break apart the ions. So the higher the lattice energy, the stronger the bond between these ions. And you remember that we can think about what causes the lattice energy to be higher using Coulomb's law. So here's Coulomb's law. This is the lattice energy. The force of attraction between the two right there is the lattice energy. So the bigger that is, the higher the lattice energy will be. So you know it's impacted by 2 things, or 3 things actually. The charge of each one of the ions. So let's say that this ion down here was +2 instead of +1. Well, that would increase the amount of charge, and so it would make the force of attraction higher, which I think makes sense. The more positive that is and the more negative that is, the stronger the attraction will be. And then down here, this is the distance between the two of them. And so the distance between the two of them, if it was actually smaller, if this was a small number, then that would cause the force to be bigger as well. And so we're looking for something with high charge, +1, +2, +3, -2, -3, and where the ions are relatively small. So let's look at our answer choices. If we go solely based on charge, well, for starters, we can certainly get rid of D. And the reason we can get rid of D is because it's not ionic at all. It's not going to be in a positive-negative pattern because it's covalent bonding. There's no metal and nonmetal. You notice carbon is here, hydrogen is there. They're both nonmetals. So this is covalent bonding. So we can get rid of that. But then the other ones, let's look at it from based on charge. You notice that lithium is +1, and fluorine is -1. So those both have low charge. Magnesium is +2 and chlorine is -1. So right away we might want to, thinking about it that way, rule out A. and then calcium is plus 2 and bromine is minus 1. So these two have the same charge setup. So let's look at them in terms of size. We have chlorine right here and we have bromine right there, and bromine is actually bigger because it's lower down the periodic table. So we'd expect the chlorine to have a stronger force because there's a smaller distance between the two of them. So right now that's kind of leading to this one. And then let's look at magnesium, and calcium is bigger than that, and then the same result occurs. Calcium is bigger, magnesium is smaller. If R is smaller, then we get a stronger Coulombic attraction. So I think the answer is going to turn out to be B here, based on those two factors. And then number 10, they want to know what the bond order for the OO bond is in ozone. Remember, the bond order is kind of a simple idea. If we had, say, that versus this versus that, this really is a bond order of 3, this is a bond order of 2, and this is a bond order of 1. And you remember, if you have something that is like, say, this, where you could have a resonance structure, you know, the double bond doesn't necessarily have to be here, it could be in each one of these places. We think of it being average, so instead of this being 2 and this being 1 and that being 1, the bond order here would be like 1 1/3 in that case. So here's another example. If we have this guy, and you remember there are carbons at each corner, instead of being a bond order of 2 and a bond order of 1 and a bond order of 2 and a bond order of 1 and so on and so forth, it turns out that since the double bond can rotate, that we really have a bond order of like 1 1/2. So that's the idea, and you notice that clearly we need to draw the Lewis structure of the ozone in order to figure it out. So let's do it. It's 3 oxygens, so we're going to spread them out like that. We've got to add up the valence electrons. Looks like oxygen's going to have 1, 2, 3, 4, 5, 6 valence electrons each. 6 times 3 is 18. We have 18 valence electrons to work with. It's a nice even number. That looks good. We're going to start on the outside. 1, 2, 3, 4, 5, 6. Keep going around the outside until they all have 8 like that. We've used 16 at this point, and we have 2 more left to go in the middle. And remember, we are not done because one of these atoms does not have 8. The one in the middle only has 2, 4, 6, and it needs 8. You remember, the only way to fix that is to share. So I'm going to grab these 2 electrons and drop them down right there. So I'm going to go get rid of these 2. Yep, get rid of these 2. There it goes. Not working there though. Anyway, and drop them down there. So that's what it's going to look like. And so we might say to ourselves, well, now that we're done, the bond order here is going to be 1 and 2. But you remember, we could have easily shared from the electrons on this side. So there is a resonance structure here. So instead of this one being 1 and that one being 2, I think that the average bond order is going to be 1 1/2. So the answer is C.